welcome back. So we were discussing sensors, especially position, velocity and acceleration sensor in the last lecture. So in this lecture, we'll discuss force torque sensor, planetary gearbox and harmonic drives. These are the transmission systems which are there in the cobots. So let us begin. So in this lecture, we'll be discussing about force torque sensors, planetary gearbox and epicyclic gearbox, that is commonly known as sun and planet gearbox as well. We'll discuss about harmonic drives, which is very widely used in cobots and the joint design also. Okay, so let us begin with force and torque sensors. So as such, most commonly used type of force torque sensors are strain gauge type of force torque sensor. When you see such sensors, there is actually a strain gauge rosette which is there inside. So it looks like this, you see the yellow one, and it has a resistive wire which is inside. You see it is something like zigzag and it comes out. So one side of it you supply the current and other side it comes out. You apply a potential difference across the electrical lead wires which are there. So actually this offers a resistance. Okay, so whole of this resistance wire is sandwiched between the layers of a resistive foil. So what happens when this is glued on top of any surface and that surface get deformed? So this strain gauge rosette also gets deformed and there is some change in the resistance, which is because of the change in the dimensions. Force sensed by such a load cell F is given by epsilon A and E. What is epsilon? Epsilon is the strain, that is change in length per unit length if it is linear change. Okay. A is the area of cross section. E is the Young's modulus of elasticity of the strain gauge material. So this and this basically relates to the Hooke's law only. Strain gauge factor, that is shown here, is given by delta R by R, change in resistance per unit resistance, upon epsilon. Epsilon is the strain which was there. Okay, so delta R by R divided by delta L by L in case of linear dimensions. So the force sensed by the load cell F becomes equal to delta R by R AE by G. Okay, where most of the terms that you see here is constant. Total resistance of this strain gauge rosette, once it is selected, that remains constant. Gauge factor remains constant, area is constant, E is also constant. So what changes here? Force is reflected directly by the change in resistance. Okay, so these are, if you look at a standard force sensor, that's a linear force sensor, it has a material, that is an elastic body, which you can see, that is here, this one. Okay, and on top of it you see there is a strain gauge rosette which is fixed here. This is the element, and these are all conducting wires. There are loose wires, they are not very tight, so that any deformation will be affected because of these wires. Okay, so that actually carries the potential to these strain gauge rosette. Okay, so when any load which is acted over here, it is transmitted to the elastic body and that body gets deformed. When that gets deformed, the strain gauge rosette gets deformed and you see the change in resistance over here in these electrical terminals. Okay, if you pack it together, it looks from externally, it looks like this. Okay, this is a Siemens make. So initial resistance is known, gauge factor is already given by the manufacturer. Okay, so all the dimensions, all the experimental things are already given by the manufacturer. Okay, so this is how it works basically. So if it is used to sense an acceleration, what you can do here is acceleration is equal to force upon m. M is the mass of the accelerating object. So you can always create a fixture where delta R by R AE by G, m is here, that is the mass of the material which is actually getting moved when you touch. Let's say it is just like a proof mass which was there earlier in sensors you have learnt. So it may be something like this. So when there is any acceleration, it would cause a kind of force. If it is moving like this, it would cause a force over here, and here is your material which may be deformed, and this is where you can put the strain gauge rosette. So this can be used to sense acceleration also. So any other secondary sensors could be a torque sensor, a pressure sensor, stress sensor, flow rate sensor. If you can put it on a differential pressure sensor across a venturi or a pitot tube, it can be used to sense all those kinds of physical values. We can enhance the properties of the force sensing. Why it is required? Because standalone sensor may be affected due to the temperature also. So this is one of the environmental factor which seriously affects the value of the resistance. So that needs to be compensated. Okay. So in order to take care of that, so we can use a kind of Wheatstone bridge that you can see here, when there are 4 of such strain gauge rosettes which are here. Each one of them forms the branch of the Wheatstone bridge. So when all the resistances are same, in that case there is no voltage that appears over here, that is the Wheatstone bridge voltage can be measured as 0. So when balanced, in case of balanced case, it is R1 by R4 is equal to R2 by R3. Okay. So in this case it is perfectly balanced and no current flows through it. So in case of unbalanced condition, that means one of the resistance changes due to the strain, so it can cause some voltage to appear and current to flow from here. Okay, in that case voltage across this terminals, that is this and this, that is the V, becomes equal to supply voltage, that is over here Vs R1 by R1 plus R4 minus R2 by R2 plus R3. So this is a standard unbalanced bridge formula. Okay, this can be derived using KVL, KCL, that is Kirchhoff's laws. Any change in the resistance due to the change in temperature now can be cancelled. So one of them is actually fitted on top of the deforming body. Okay, and other one is a dummy one which is only there to sense the change in temperature. So temperature affects both the arms equally. Okay. So instead of using just one strain gauge rosette, now you can use 2 or all 4 of them. There are various configurations to show this. So it can be a quarter bridge strain gauge circuit in which only one is used. This is not preferred because this cannot do temperature compensation. Other one could be quarter bridge strain gauge circuit with temperature compensation. One bridge is unstressed. So one of them is fixed on the beam, other one is not stressed but it is there in the same environment. Okay, so there would be no change in that resistance, the one which is not fixed to the object which is getting deformed, but it will see the change in temperature. Okay, this is other arrangement. And the third one is half bridge strain gauge circuit. 2 are used, one is under tensile load, other one is under compressive load. Okay, only 2 are used. The final one is the full bridge strain gauge circuit as shown in the figure, in which all the 4 are fitted. So 1 and 3, if it is force like this, comes under compression, whereas the top 2, 2 and 4 will be under tensile load. Okay. So this is elongated, whereas the bottom one will get compressed. Okay. So these are the 4 ways you can put this to measure the change in voltage. So voltage change will appear here due to change in all of them. Okay. So now in case of quarter bridge configuration, initially R1, R2, R3 and R4 all are same, and the voltage in that case would be supply voltage by 4 delta R by R. If you can substitute delta R by R to the gauge factor and epsilon, it comes here like this. Okay. So gauge factor into epsilon is actually equal to delta R by R. Epsilon is the strain, and strain can be replaced by F by AE. AE are the cross section area and E is the Young's modulus, F is the applied force. So now you can notice that voltage output is directly proportional to the force. Higher is the force, higher is the voltage that you see here at the bridge. Okay. For a general purpose foil strain gauge, G is equal to 2. Modulus of elasticity is equal to F by A by epsilon as per the Hooke's law that you already know. So in case of full bridge strain gauge circuit, which is rarely used, it is not required. 2 of them is quite good enough. Okay. One of them can be in tension, other one could be in compression, or one of them is glued, other one is just in that environment. So those two are most commonly used configuration to do temperature compensation. In this case, full bridge strain gauge circuit, all the 4 resistances are used. So in that case it is this, okay, 1 by 4 times of all the strain that will be visible here. Change in resistances are shown here. This may be written as 1 by 4 gauge factor into epsilon 2 minus epsilon 1, epsilon 4 minus epsilon 3. For a half bridge, that is in arms 4 and 1 or 3 or 1, in this case epsilon 3 is equal to epsilon 2 or epsilon 4 is equal to epsilon 2 as 0. Okay. So in case you are using only 4 and 1, 2 and 3 becomes equal to 0. In case 3 and 1 is used, 4 and 2 would become equal to 0. If at all these 4 strain gauge rosets are fitted on a shaft which is having a torsional load like this, these gauges can be fitted like this: 1, 2, 3 and 4. Okay. In this case what would happen, it is basically a 45-degree 4 helix gauges on the shaft that is fitted. So in this case, if it is having a torsional load the way I have shown here, what would happen? Number 4 and number 1 would come in compressive load. Okay. So these two would be in compression. Okay. So this one will be in compression. And what would happen to number 3 and number 2? Those two will be in tension. Okay. These two will come in tension. Okay. So the deformation occurs accordingly. So if you reverse the direction of torque, opposite would happen. In that case 1 and 4 would come in tension and 3 and 2 will come in compression. Okay. So this is how the deformation can take place. So you can have 4 such gauges again put on a shaft and you can measure the torque. In that case the torque is given as tau is equal to V, that is the voltage that is sensed here, and Vs, that is the source voltage which is here, and then G is the gauge factor for the strain gauge, R is the radius of the shaft, okay, E is Young's modulus of elasticity of the strain gauge material, this is Poisson ratio. So overall this can be expressed, J is the polar moment of inertia. So you can measure torque. So you can have multiple arrangement of these gauges on such systems and you can have your own derivation for this formula and you can calculate the torque accordingly. Okay. So this is for one such arrangement and it can measure the torque. Okay. So now if at all you have arranged in a manner when you have 6 such sensors, such strain gauge sensors which can give 6 outputs across some arrangement. Okay, it may be 4 bridge arrangements which may be something like this you have. So if you can put your strain gauge somewhere over here, somewhere over here, somewhere here and somewhere here, or maybe some other places also, there are various arrangements that has been experimented out. So based on the voltages that is seen by different sensors over here, it can have a relationship between the forces Fx, Fy, Fz, this becomes a 6D sensor, that is 3 for the forces along x, force along y, force along z, okay, z also will deform it. So there will be multiple deformations even for the single load, okay, unidirectional load along any axis will change the voltages to all the gauges, okay. So that is the reason it's a complex relationship. There is a gauge calibration matrix which is 6 cross 6 matrix that relates the voltages those are seen by the 6 strain gauges to the forces and moments that are appearing here. So 3 axis force and all 3 axis moments can be related to the voltage using 6 cross 6 gauge calibration matrix. Sensor output voltage and force and moment are here. So such calibration matrix relates the sensor output voltage to the forces and moments. A 6 axis 4 stalk sensor looks like this, when you can see Fx, Fy, Fz, Mx, My, Mz. So you have a built-in electronic circuit inside that actually does the conversion. It has a pre-calibrated gauge calibration matrix inside. It checks the voltages, multiplies it to the gauge calibration matrix, and finally it gives you directly the force and the moments, okay. So this is how this can be designed. So a torque sensor may look like this. So it is a simple arrangement in which you see there are strain gauge rosets which are fitted at this location, over here, and here also. So all the 4 places it is there. So this is a single axis torque sensor about the axis which is like this. So this directly can be seen and it looks like this, and you have electronic circuit which is here that takes up the signal, does some filtration, conditioning of the voltages, and finally it multiplies with the gauge calibration matrix if at all it is required in case of 6-DOF sensor, okay, and it gives you a pre-calculated form of the forces and the moments, okay. So a joint torque sensor which is there in the cobot, it looks like this, okay. So now let us come to transmission that is used in cobot. So it can be a planetary gearbox or it can be a harmonic drive. So we'll look at them one by one. So let us see. So a planetary gearbox is commonly known as a sun and a planet gear system. In this case, you see you have a rotating shaft. This is the sun gear from where you can provide the input, okay. So this rotates, okay, like this, let us say, as it is shown in the yellow over here, okay. If this rotates like this, so all the planets that are there, planet gears which are there are 4 over here, 1, 2, 3 and 4, they will rotate opposite to this. So if yellow one is rotating like this green one will rotate in opposite direction, and this will now roll over the gear which is known as a ring gear, okay. So it rolls over that, and finally each one of them will move like this, okay. So they move like this, all 4 of them, they will move like this. So the frame which holds these 4 gears, those the planet gears, so that frame rotates, okay, that becomes the output shaft. So input shaft is the sun gear, output shaft becomes the frame which holds the planet gears. Let us see a quick video on this. So you can see how it is rotating. Let me just wind it up once again. So you see how it is working. Got it? So the frame which is holding the planets is rotating. Finally, that is appeared as an output shaft. So output shaft is rotating along with the planets, okay, and sun becomes the input. So this is how it works, and the gear ratio lies between 3 to 10. If it is 3, that means sun gear is very small, okay. In that case the output becomes very slow, okay. But if the sun gear size is increased, it can go up to 10 times of gear ratio. So input to output, actually it becomes 10 times of reduction, okay. It is reduction basically. Output becomes less than the input. Output angular velocity is less than the input. So it is depending on the size of the sun. You cannot make it too big or too small, so that limits the gear ratio to 3 to 10, and it becomes almost like a direct drive because there is hardly any loss over here. So these are the advantages. Input shaft, that is over here along with the sun gear center axis. So that is the input shaft, and the output shaft you saw, that is center of all the 4 planet gears, that becomes in line with the input shaft. So output and input, they become in line, okay. This is very compact, and you can have multi stage of these kind of gears. So output can again get into the next stage of the sun gear, and finally the output of planet gear of the second stage becomes the output. So you can have multiple such modules one by one in series, and you can have higher gear ratio also, okay. Because it is aligned to the center, there is very less vibration and a high amount of torque can be transferred, okay. They are very efficient as compared to the standard gearbox, which has gears, they are one after the other in a serial chain, okay. So this is the working of a planet gear, and this is the gear ratio, okay. This is how it works. You have seen the video. Now let us come to harmonic drive. This is again very commonly used in cobots. It consists of 3 major parts. First one is the wave generator, that is the input shaft, and it is not circular as it appears, it is actually elliptical, okay. This is elliptical. And the second part is the flex spline, that is the output, that finally would become the output from here. From here it takes, output shaft is connected, and it is known as flex because this is made up of a flexible drum kind of, it is flex, okay. You will see the working also. And finally it is having a circular spline, this is rigid, and it has internal gears, okay. So now let us just run the video once again. So this is the complete assembly which is shown. All the 3 parts are dismantled now. So this is an ellipse, you see, this is an ellipse, okay. It is elliptical, and this is the input shaft as well. You have noticed it. Now this will get into the flex spline. This is the flex spline. It is like a drum, and it is flexible also. And this is the circular spline that has the internal gear, and this is rigid. Okay. Now when everything is assembled, see, this goes into this one, okay, and when this will rotate, okay, it will deform the flex spline, it will make it elliptical, and the axis of elliptical rotates inside, and that rolls over the internal gear of the circular spline. As it rolls, it also moves because number of tooth in the flex spline is less as compared to the circular spline. Tooth is less, So see, it is rolling and the input shaft is shown, and you can now see the output shaft that is rolling and it is rotating very slowly. Now the gear ratio of this would be number of tooth in the flex spline minus number of tooth in the circular spline, which is here, divided by number of tooth which is there in the flex spline. Okay. So for circular, let us say there are 202 circular spline tooth, and in flex spline there is 200 tooth. In that case, if you put that, you will get it is minus 0.01. Minus sign indicates that the input and output are directed opposite. If it is clockwise input, output shaft will rotate counterclockwise, and the gear ratio is 1/100 times. Got it? So it has a high gear ratio in such a compact form. Okay. So that is the beauty of such harmonic drives. So there are many advantages. Again, you see both the input and output shaft are coaxial. Okay. They are very compact and light, and you saw it has a center hollow also. You can pass the wire from its center. So if you have a BLDC motor, if you have a harmonic drive, you can create a closed loop circuit, that is the controller with a center hollow design. So if it is all assembled together, it creates a center hollow servo drive. Okay, this also has a very less vibration, and it has, you saw, very high gear ratio can be created in a compact way, and high torque transmission is also possible. They are very efficient, and practically there is no backlash. This is one of the most advantageous thing which is looked at when you make any robot. So in case of other gear systems, you would need some other arrangements to take care of the backlash, using some preloaded torsional spring or some kind of other mechanical arrangements, but this does not require any such arrangement, and it practically has almost no backlash. Okay. So this is how an harmonic drive works, and this is the gear ratio. These are some of the advantages. Okay. Only thing is, manufacturing of this flex spline is not that easy. Okay. And that is the reason very few manufacturers are there. Okay. Altogether now, we have already discussed the torque sensor, we have discussed link position sensor also. Harmonic drive you have seen just now, it can be a planetary gear also. You have also seen a BLDC motor with Hall effect position sensor, it can go somewhere over here. And now we need to discuss on the controller and other aspects that will come later in this course. Okay. So overall we have covered till here. That's all for this lecture. In the next lecture, I will discuss industrial field bus, drives, devices, safe workspaces, safety triggers, workspace monitoring, marking forbidden zones. Thanks a lot.